Welcome to the fascinating world of sound, a realm where invisible waves shape our daily experiences. In this video, we'll embark on a journey through the physics of sound, exploring how vibrations become the music, voices, and noises we perceive. From the moment sound is created to its final reception in our ears, each step is a marvel of nature and science. Whether you're curious about why thunder follows lightning or how a guitar string sings, this guide will illuminate the invisible symphony all around us. Let's dive in and discover what makes sound so essential and intriguing. Sound is not just a sensation, it's a form of mechanical energy. Unlike light, which can travel through a vacuum, sound needs a material medium like air, water, or even solid objects to move. This requirement is why you can hear someone knocking on a door but not shouting in space. The energy of sound is carried by particles bumping into each other, transferring the vibration from one to the next. This simple yet profound fact underpins everything from music to communication. Without a medium, sound simply cannot exist. Classic demonstration of sound's dependence on a medium is the bell jar experiment. Imagine a bell ringing inside a glass jar. As air is gradually pumped out, the ringing fades until silence prevails. This happens because in a vacuum there are no particles to carry the sound waves. Astronauts on the moon face a similar challenge. They can't talk to each other directly and must rely on radio waves, which don't need a medium. This experiment elegantly proves that sound is truly a mechanical wave. Sound travels through a process called propagation. When a source vibrates, it pushes nearby particles, causing them to oscillate back and forth. These particles don't travel across the room, instead they pass the disturbance along like a relay race. This movement forms a longitudinal wave where particles move parallel to the direction of the wave. It's different from transverse waves like those in water or light, where particles move perpendicular to the wave's direction. This distinction is key to understanding how sound behaves. Truly grasp sound, we need to measure its invisible features. The wavelength is the distance between two compressions in a sound wave, while frequency tells us how many oscillations occur each second. The time period is the duration of one complete oscillation. These measurements help us quantify and compare different sounds, from a deep drumbeat to a high-pitched whistle. Understanding these properties is essential for fields like music, engineering, and even medicine. Sound doesn't travel at the same speed everywhere. Its velocity depends on the medium, faster in solids, slower in gases. For example, sound moves at about 344 meters per second in air but can exceed 5,000 meters per second in steel. Temperature also plays a role. On a hot day, sound travels faster. This explains why you see lightning before you hear thunder. The light reaches you almost instantly, while the sound lags behind. These differences are crucial in everything from engineering to weather forecasting. Pitch is how our brain interprets the frequency of a sound. High-frequency waves create high-pitched sounds like a whistle or a soprano singer. Low-frequency waves produce deep, low-pitched sounds such as a drum or a bass guitar. This relationship between frequency and pitch is fundamental to music and communication. It's why different instruments and voices have unique tones, and why we can distinguish between a child's voice and an adult's. Loudness and intensity might seem similar, but they're not the same. Loudness is a subjective experience. It's how strong a sound feels to our ears, and it depends on the amplitude of the wave. If you double the amplitude, the loudness increases fourfold. Intensity, on the other hand, is an objective measurement. It's the power delivered per unit area independent of our hearing. This distinction helps explain why some sounds feel louder than others, even if their physical intensity is the same. Let's compare soft and loud sounds. A soft sound, like a gentle whisper, has a low amplitude. A loud sound, such as a shout or a siren, has a high amplitude. The difference is not just in how we perceive them, but in the energy they carry. Loud sounds can travel farther and have a greater impact, while soft sounds are more subtle and intimate. This principle is used in everything from music dynamics to designing quiet spaces. Sound waves, like light, can reflect off surfaces. This reflection is governed by simple laws. The angle of incidence equals the angle of reflection, and both waves and the normal lie in the same plane. These principles are put to use in concert halls, where curved ceilings help distribute sound evenly, and in stethoscopes, which guide sound through tubes to amplify heartbeats. Megaphones also use reflection to direct sound energy forward, making voices carry farther. Echoes occur when sound reflects off a distant surface and returns to our ears after a delay. For our brain to perceive a distinct echo, the reflected sound must arrive at least 0.1 seconds after the original. This means the reflecting surface must be at least 17.2 meters away. Reverberation, on the other hand, is the persistence of sound due to multiple reflections, making speech or music linger. While some reverberation adds richness, too much can make speech unintelligible. Excessive reverberation can make it hard to understand speech, especially in large rooms. To solve this, materials like heavy curtains, compressed fiberboard, and rough plaster are used to absorb sound. These porous materials trap mechanical energy, preventing it from bouncing back and forth. By carefully designing spaces with sound absorption in mind, architects and engineers create environments that are both comfortable and acoustically clear. Sound waves come in a wide range of frequencies. The human ear can hear sounds from about 20 Hz to 20,000 Hz. Below this range is infrasound, which we feel rather than hear, and above it is ultrasound used in medical and industrial applications. Interestingly, children and some animals, like dogs, can hear higher frequencies than adults. This spectrum of sound is the foundation for technologies like ultrasound imaging and animal communication. Ultrasound waves, with frequencies above 20,000 Hz, have many practical uses. In medicine, they create images of the heart and other organs through echocardiography. In industry, ultrasound detects flaws inside metal structures and cleans hard-to-reach parts. These applications rely on the ability of ultrasound to penetrate materials and reflect off internal features, revealing hidden details that are invisible to the naked eye. Sonar, or sound navigation and raying, uses sound waves to detect objects underwater and measure distances. A transmitter sends out a pulse, which reflects off the seabed or an object and returns to a detector. By measuring the time taken for the echo to return, the depth or distance can be calculated. This technology is vital for submarines, ships, and even mapping the ocean floor, showcasing the power of sound beyond our everyday experience. Ears are remarkable biological receivers, designed to capture and interpret sound waves. The outer ear collects sound, which travels down the canal to the eardrum. Vibrations are amplified by tiny bones, the hammer, anvil, and stirrup, before reaching the cochlea, where they're converted into electrical signals for the brain. This intricate process allows us to enjoy music, communicate, and stay aware of our surroundings, highlighting the incredible synergy between physics and biology. Wrap up, let's review the essential formulas and relationships in sound physics. The speed of sound is given by the product of wavelength and frequency. The time period is the inverse of frequency. For echoes and sonar, distance is calculated using the speed of sound and the time taken for the echo to return. Remember, pitch is tied to frequency, loudness to the square of amplitude, and the audible range for humans is 20 Hz to 20,000 Hz. These principles form the backbone of our understanding of the invisible symphony that surrounds us.